Good afternoon, everyone. I would like to welcome you to section number 2. The chair of this section will be Professor Oren Lavan from Israel Institute of Technology in Israel, and as co-chair Madalena Ponte from Instituto Superior Te in Portugal.
Thank you for the introduction. Shall we start? Yeah. Okay, so before we start, I would like to take the opportunity and to thank Rita and the organizing committee for hosting this workshop at these rather irregular times that are irregular both in elevation and in plane and stiffness and strengthening irregularity and whatever you want. So we will start the next session. So we don't have the first speaker yet. So can we switch between the first and the second lectures?
I believe Juan is already here.
Yes, I am. I'm ready.
Okay, so let us start with the second presentation, and then we will go back to the first one if the presenter is here. So Madalena, would you like to present the next talk?
Yes. So Juan will be presenting his paper about evaluation of torsional parameters in seismic code provisions for multi-story and symmetric planned buildings.
Thank you very much. I am Juan Carlos Reyes. I'm associate professor at Universidad de los Andes in Colombia. My other co-authors are Luis Ardila and Maria Paula Moreno. They were my students. I'm going to talk about the evaluation of torsional parameters in seismic code provisions for multi-story and symmetric plan buildings. This is a work. I presented some advances in the last workshop. Well, I'm going to present this time the full research we did. So first question here is how we qualify torsional irregularity in a building like the one shown in the left, or even in this one here. So what kind of parameter should we use to quantify if this building is classified as irregular in plan, or if it has torsional irregularity? So going to the current provisions in the US, those provisions are based on linear spectral analysis. When you have a building like this, you take, for example, the J's floor shown in yellow. And this is like the deformed shape of that floor. If you plot the next floor, so you will see, you can measure the drifts between the two floors. So you will see a minimum drift in one side and a maximum drift in the other side. So you could calculate a factor to quantify the level of torsion. This factor, I call it here alpha, just to put a number and a name to that factor. And it's calculated as the maximum drift divided by the average drift, the average between the maximum and the minimum. So with this factor, this code quantifies the level of torsion using the following ranges. If you are between 1 and 1.2 in this area, you will have no torsional irregularity, but then just after 1.2, you will have torsional irregularity in this range, and then you will have extreme torsional irregularity for the last range. So this is the kind of decision we can make to quantify the level of torsion in this code. Also, the accidental torsion is affected by this decision. So this factor AX is defined in the code to increase the accidental torsion. So if I plot the numbers here, you have 5% of accidental torsion for no torsional irregularity buildings. And then after that, you will increase that. For example, 1.4 alpha will be associated with 6.8% of accidental torsion. That's a torsion that we need to add to the itself to the other torsion that the building already has. So to evaluate this parameter, we selected these buildings that are shown here. We have some rectangular buildings, some L-shaped buildings, and some T-shaped buildings of 5, 10, and 15 stories. Here I'm writing the alpha number. As you can see, all the buildings in this first row don't have any torsional irregularity, but the buildings in the second row and the third row have some, and especially those at the bottom, we have extreme torsional irregularity with an alpha factor larger than 1.4. We selected some ground motions. Initially, we take the ground motions as they were without any scaling factor, a scaling factor of 1. And then we got this level here for the median, the intensity. Then we multiply by a factor of 3. We got a level similar to the design level for the median. And then we increase it by a factor of 4 to go even beyond the design level. So here I'm showing in dashed lines the design level, this one here, and the one here is divided by the R factor. So you will see that basically the scaling factor of 1, we have some very basic inelasticity, but the factor of 3, we have a lot of inelasticity for the building. Modal participation of these buildings are one of the first parameters we try to evaluate, because you may think that just using the modal properties, you may identify the level of torsion. Here, I'm showing for the rectangular, the L shape and the T shape for the 5, 10, and 15 story before, how those are distributed, the participation factors, participation mass for the first, 2, and 3rd mode. So you will see, for example, for this building, how the participation mass for the first mode is very low. And it also have a lot of coupling with the translation in X and Y, and also with torsion. And this is kind of interesting, and you will see that you may think that this may be important, and using this kind of information, you may decide if the building has torsional irregularity. But then this part is confusing here, because for this building with a larger alpha factor, the first mode and the second mode may have a lot of participation, the mass in one direction. So it's not, we don't see the same situation for all the buildings. So first we try to use this result as a parameter to quantify torsion. So plotted here is the first mode effective mass and against the total mass, and horizontal axis of the alpha factor. So you will see that the rectangular plans are well aligned here with very large participation mass. And even this building with an L shape that has no torsional irregularity is still okay. But when you go to the other buildings, you will not have a clear trend. You will see somehow that participation is lower for the first mode, but it's not a very easy parameter to evaluate the level of torsion in a building. So then we went to do the evaluation for the parameter, alpha parameter, included in the code, in the American code. So with this parameter, I'm plotting here the ground motions in the horizontal axis and increasing alpha factors evaluated in the X direction of this building. X direction for this T building, for example, is the one that has the most torsion, the most torsional behavior. So the calculated factor alpha using linear analysis is 1.4. And now here using a nonlinear dynamic analysis, plotting all these dots, you will see that in general, most of them are close or near, sometimes below or above the value calculated using linear analysis. If you go to the other direction, the building will have an alpha of 1.1, so no torsional irregularity will happen here. You will see similar behavior for the nonlinear response history analysis, although for some ground motions, very intense ground motions, you will see some points that may predict torsional irregularity. And again, this is for individual ground motions, and usually you don't rely completely on individual ground motions. So then I was trying to evaluate if the linear analysis or the level of elasticity will change the alpha factor. So plotting here is the maximum drift against the alpha in X direction. So you will see that, for example, for a factor of 1, the red points, all of them will have the same dispersion of a factor of 3 the black points, or a factor of 4, the cyan points here. So in general, you will not see that the level of inelasticity will affect the alpha factor. So this factor is kind of robust and doesn't depend much on the inelasticity level of the building. So here I'm also plotting the same information for the other direction. In this, we have a little more dispersion. But again, you will see that the values isolates around the one calculated using linear analysis. So in conclusion, model properties are not sufficient to quantify the level of torsional response, and the torsional ratio alpha has a small variation with respect to seismic intensity level and shows low record-to-record variability. And because of this, we consider this torsional ratio alpha is adequate to identify plan irregularity of multi-story buildings. So these are like the main conclusions. We have done this for all the buildings, but only showing here the T10, which is one of the most critical ones. Thank you very much for your attention.
Thank you for your presentation. It was really interesting. I think nobody has questions or raised his hand. So
if no one has any questions, then I will ask a short question. Juan, have you looked at nonlinear structures, or do you plan to do that?
Yeah, the structures are nonlinear. Like you see,
okay.
We here at the beginning, let me go here. We try different intensity levels. So we try a scaling factor of 1, which is mostly linear, but then this scaling factor of 3 and 4 are will go or take the building very far into the inelastic range.
So how is the strength distributed in these cases of nonlinear?
Oh, the buildings are frame buildings, are steel frame buildings, and they have some frames in the perimeter here, as is usually done in the US. So all the plasticity comes from the yielding of the frames, especially beams and some columns in those frames.
Okay, thank you.
Perfect.
and for these buildings, you only consider the irregularity in plan. You didn't consider the irregularity in height, or did you model the infills for these case studies?
Yeah, in this case, we were interested only in torsional irregularity in plan. So only is restricted to in plan. That's why we are using this alpha parameter here, which only includes the level of torsion in plan. And we are not including the effect of the infills. Usually in the US, at least, these steel buildings have partitions that are not fragile. So we are not including that effect here.
Okay, thank you.
Okay, thank you. We will move to the second presentation, which is actually listed as the first one in this session. It will be given by Professor Konstantinos Kostinakis, entitled Evaluation of the Effectiveness of Accidental Eccentricity in Capturing the Effects of Irregular Masonry Infills. Please go ahead.
Yes, thank you very much. We had some technical problems here, but now we're okay. So the title is Evaluation of the Effectiveness of Accidental Eccentricity in Capturing the Effects of Irregular Masonry Infills. Reinforced concrete buildings with unreinforced masonry infills is a very common construction strategy in case of many regions characterized by high seismicity throughout the world. Okay. So nevertheless, due to the uncertainties related with the appropriate modeling of the infill panels, their effect on the RC structural elements, and consequently their impact on the seismic behavior of the buildings is often not taken into account. Thus, the infills are usually accounted for as non-structural elements and are neglected in the process of buildings analytical modeling. The above approximation has been adopted by current seismic code provisions, which give only a few general guidelines for the proper deal of the non-structural elements. These guidelines are often insufficient, incomplete, and not adequately clarified. Nevertheless, a large number of experimental and numerical researches, as well as the observation of post-earthquake damages, have shown that the masonry walls in many cases tend to interact with the surrounding structural elements when seismic loads are applied to the buildings, resulting in significant modification of the structural behavior. The non-uniform placement of the masonry infills is usually made for functional reasons, causing to the RC buildings significant irregularities. Such irregularities may cause important increase of the seismic vulnerability, or even in some cases disproportionate structural damage or collapse. This is the reason why a lot of research investigations in recent years have focused on the seismic assessment of buildings with irregular placement of masonry infills. The Eurocode 8 states that strongly irregular, unsymmetrical, or non-uniform arrangements of infills in plan should be avoided. Moreover, the same code suggests that in the case of masonry infills irregularly distributed, these irregularities may be taken into account by increasing by a factor of 2 the effects of the accidental eccentricity. In the present paper, the need to increase accidental torsion in nonlinear seismic analysis as a parameter to capture the effects of the infills irregularities is further investigated through the evaluation of a multi-story 3D RC building with irregularly placed masonry infills. The seismic assessment of the building is carried out using the nonlinear pushover analysis according to the Eurocode 8 provisions. Two different structural models are investigated. A model taking into account the masonry infills as diagonal struts, and a model without taking into account the infills, but increasing by a factor of 2 the accidental eccentricity as Eurocode 8 proposes. Then a comparison between the two models is carried out in order to examine the effectiveness of the accidental eccentricity in capturing the effects of irregular infills. For the analysis conducted, a reinforced concrete building consisting of 5 stories and a basement is considered. The building is located in the city of Thessaloniki, Greece, and was constructed in 1960 without fully modern seismic code provisions. The plan view of the building stories, as well as the dimensions and the longitudinal reinforcement of the structural elements, are shown in the figure. The main load-bearing structure consists of beams, columns, as well as a reinforced concrete core wall. The foundation of the building consists of individual footings and connecting beams. For the modeling of the building, all basic recommendations of Eurocode 8 were taken into account, and the building was analyzed by means of nonlinear pushover analysis as defined in Eurocode 8. In order to model the nonlinear behavior of the structural elements, plastic hinges were placed at the column and beam ends as well as at the base of the walls. The properties of the plastic hinges were defined according to the code provisions of Eurocode 8 and the Greek Code of Interventions, AMEP. The masonry infills were modeled according to the provisions of the Greek Code of Interventions. More specifically, each infill was modeled as an equivalent hinge diagonal strut compression with a given wide beam. The mechanical properties of the infills were estimated using the mechanical properties of the bricks and mortar and taking appropriately into consideration the method of masonry construction. The geometrical properties of each strut were determined using the relative code provisions of ANEP. The building was assessed using the non-linear pushover analysis according to the Eurocode 8 provisions. The following different structural models were investigated. A model without taking into account the infills and using the value of the accidental eccentricity proposed by most seismic codes, that is 5% of L, whereas the floor dimension perpendicular to the direction of seismic action. A model without taking into account the infills but increasing by a factor of 2 the accidental eccentricity. Two models with masonry infills distributed irregularly in plan in such a way that asymmetry along x-axis is caused and taking into account the infills effect as diagonal struts according to the modeling procedure presented. And finally, two models with masonry infills distributed irregularly in plan in such a way that asymmetry along y-axis is caused, and taking into account the infills effect as diagonal struts according to the modeling procedure presented. The above structural models were subjected to nonlinear pushover analysis, and all the structural elements of each model were assessed for bending and shear according to the provisions of Eurocode 8. For the nonlinear pushover analysis, the following assumptions were made. Limit state of significant damage, knowledge level of normal knowledge, horizontal elastic spectrum as defined in Eurocode 8 for PJ 0.24G, two different lateral load patterns, uniform model, target displacement according to the Annex B of Eurocode 8, assessment of the capacity of each structural element according to the Annex A of Eurocode 8, Part 3, and the combination of the effects of the seismic actions components according to the Greek Code of Interventions. Now let's see some results. The figures on the slide illustrate indicative results of the analysis. The results are presented in terms of percentage of bending and shear failures at the structural elements critical sections. More specifically, the figures present the results from models with accidental eccentricity 5% of L, with accidental eccentricity 10% of L, and for the models with infills distributed irregularly in plan in such a way that asymmetry along x-axis exists, under seismic actions along y-axis for mass in position μ1. The left figures regard the results for uniform lateral load pattern, whereas the right figures the results for modal load pattern. From the figures, we can see that in most cases, the consideration of the masonry infills in the structures modeling leads to larger number of bending and shear failures. However, the increase is rather small. The analysis revealed that the number of shear failures is much larger than the one of bending failures, something which was expected since the investigated building was constructed according to old codes without seismic provisions at capacity design. Moreover, practically no difference has been noticed between the models with small and large infills irregularities. Now, considering the comparison between the models with accidental eccentricity 5 and 10%, it can be seen that when the accidental eccentricity is multiplied by a factor of 2, as Eurocode 8 proposes, the damage is more severe. However, the difference between the two models is rather small. See, for example, that in case of the building under modal load pattern, 14.5 and 81.6% of the critical frame sections have failed in bending and shear respectively when the accidental eccentricity is 5% of L, whereas the respective percentages in case of the W value of eccentricity are 18 and 84.2%. This observation leads to the conclusion that the provision of Eurocode 8 would suggest increase of the accidental eccentricity in order to account for the irregular placement of the infills was proved to be effective up to a point, since it failed to capture adequately the effects of the irregularities on the infills distribution for the model which we analyzed. The adequacy of this provision depends on the analysis, namely the direction of the seismic action, the load pattern, and the mass position. It must be noticed that similar results have been found for the whole number of the analyses conducted in the study. Now, based on the results of the study, the following general conclusions can be drawn. In most cases, the consideration of the irregularly distributed masonry infills in the structures modeling leads to larger number of bending and shear failures. However, the increase is rather small. Moreover, practically no difference has been noticed between the models with small and large infills irregularities. The increase of the accidental eccentricity by a factor of 2, as Eurocode 8 proposes, leads to more severe damage for the studied building. However, this provision of Eurocode 8 was proved to be effective up to a point, since it failed to capture adequately the effects of the irregularities in the infills distribution for the investigated building. Thank you very much for your attention.
Thank you for the presentation. I have not seen any questions in the chat, nor anyone raising his hand or her hand. Does anyone have any questions about this presentation? If not, then I will ask a quick question.
Yes.
So the structure you considered is highly irregular in plan. How do you think the conclusion would change, if they would change, if the structure was symmetric, for example, because the accidental eccentricity doesn't add too much of eccentricity to this specific structure, whose eccentricity, built-in eccentricity is very high. But small eccentricity added to a structure that is symmetric, for example, may change the results more considerably.
Yes, you're right. It depends on the structural eccentricity. But I don't know what would be the result in this case. I think that the problem is very good parametric. So much research must be done in order to come to reliable conclusions, because the distribution of the masonry infills is chaotic. I think can be very chaotic. We cannot follow some certain patterns. So I think that much more research must be done in order to come to reliable conclusions. These certain conclusions have been drawn on for this building.
Thank you. So are there any other questions? No. Okay, so we will move to the third presentation that will be given by Vitor Camacho on the multi-objective optimization of long irregular RC buildings piers subjected to strong motion and definition of classification tree surrogate models. Please go ahead.
Is everyone seeing my presentation?
Yes.
Okay. Okay, so what all of this means, what this large title means is that basically what we did here was to apply multi-objective optimization techniques to design long irregular bridges in terms of pier lengths. And but we didn't stop there. So we went one step further, and we used the whole history of the optimization search to try to extract some more knowledge from the analysis that were done. This was done because when applying these kinds of algorithms, a lot of work is done analyzing structures to reach, let's say, some final results, and it's a way, using the whole history is a way to take more advantage of the big amount of processing that is made that otherwise would more or less go to waste. So why is this important? Why is this interesting for irregular structures? In the case of long bridges, long irregular bridges, it's difficult they are difficult to analyze and design due to uncertain seismic behavior. This stems from having influence from higher modes, and this leads to having needing to use most of the times nonlinear dynamic analysis, or at the least using adaptive pushover techniques. And for this reason, many design methodologies are not easy to employ for bridges, which leads to these bridges being designed through some sort of trial and error based on the experience of the design engineer. Yeah, so, okay. when designing a structure, one attempts to optimize some aspect of the structure, even if implicitly. When designing, you know, some sort of structure, either implicitly we attempt to either maximize resistance, but without using too much material, and usually these two and many other possible objectives are done implicitly and sometimes even explicitly when designing structures. So it makes sense to apply multi-objective techniques for structural optimization due to that implicit goal. Whoops, okay, wasn't supposed to go to that slide yet, but okay, so why genetic algorithms for seismic design? So in essence, genetic algorithms are meta-heuristic methods that allow to achieve optimization and are good to apply to seismic design and structural design, because traditional optimization methods aren't usually very good to apply due to the non-convex and many times discontinuous nature of the optimization problem. And these types of algorithms have no trouble with discrete search spaces due to discrete variables, due to non-convex shapes of the optimization problem. And so this can be applied, and they are especially valuable for multi-objective problems where you want to obtain a trade-off between different objectives. So if you want to optimize at the same time towards performance, but also towards cost, these two objectives are not easy to optimize at the same time. Usually one contradicts the other. And so these types of solutions are useful in those cases. So okay, so in this case, what we did was we applied these optimization techniques to a case of a long irregular bridge, and this type of bridges is particularly complex because they have short central piers, and they tend to have a transverse horizontal displacement profile that is different than the usual parabolic first mode shape, and so they have a lot of influence from higher modes. So as said in this work, the objective is to apply these techniques and use the search history for knowledge or rule extraction. And the decision variables, or rather the design variables used in this instance were pier diameter, flexural steel reinforcement, and pier deck connection. And what was done was dividing the piers into groups that were somewhat similar in terms of pier location and pier size. And so those piers, in those four groups, have have the same design. And then the optimization algorithm, what it will do, it will test a lot of different combinations and a lot of different solutions of bridge instances with this initial with this typology, and will compare them based on two fitness functions that are on the one hand performance, and the performance here is the comparison of the concrete admissible strain at each pier versus the concrete strain that sets in at any point in time of the seismic action. So the method of analysis was nonlinear dynamic analysis with real strong motions, and to deploy this, Open Seas MP was used, and the reason why the Open Seas MP, the variation for parallel processing was used was exactly due to the huge amount of analysis that had to be performed to obtain this final result. We can see here in the image on the right hand side, each point corresponds to a bridge instance that was analyzed through dynamic analysis. And so we have the green solutions are feasible solutions, feasible in terms of at no point has any of the piers recorded a concrete compressive strain that was lower from that was in absolute value higher than the limit for the concrete strain, and in the blue solutions are exactly what we obtain from a multi-objective optimization, and that is called a Pareto front, where the blue solutions represent solutions that are equivalent in the sense that there is no other solution in the set that is simultaneously better for both objectives than that solution. And so if we pick up the solutions from the blue set, we have all the possible, not all, but most of the trade-offs that this optimization run caught in terms of performance and cost. And to get a grasp on why this is interesting, particularly for nonlinear, particularly for irregular and for irregular structures, and in this case, long irregular bridges, is that many times when designing, we don't get the opportunity to search a lot of different variations in the design, and this allows to catch different schemas for design, if you will. So in this case, we can see that there were two ways of designing this bridge that gave good results, and we can either decide to place let's say fixed connections in the middle short piers, or we can actually do the other way around. We can actually do monolithic connections on those piers and have the others fixed, and play with the amount of flexural steel that we place in each situation. And then we have two different approaches that basically arrive to a viable solution. And this is where it is interesting, because it allows to explore other solutions that many times are not as obvious or that kind of walk away from what is expected, and this allows to gain some insight many times on what is behind certain let's say structural behaviors. But the interesting thing was that going further from only analyzing the solutions given from the Pareto set, one can actually do something more interesting, which is after these analyses, we have tens of thousands of bridge instances that were tested. Some failed, some managed to be feasible, and if we apply, for example, in this case, we applied the classification trees. We are able to see which variables or which features are more significant for the resistance of the bridge, and in which cases. And we can clearly see which are the characteristics that are more significant for knowing if a bridge is going to be feasible or not. And that is what we get here in the classification tree on the right hand side, where in the first node we have, for example, effective stiffness of some of the effective. The sum of the effective stiffness of all the piers divided by the length of the bridge, and then this feature here, N norm, is the normalized axial force at the piers, and then we have for instance the stiffness of the third group of piers, which is the group of piers that are adjacent to the short central piers. And this is interesting because it allows the engineer to get a grasp on what actually influences the fail or success of a design, and it allows us to extract some knowledge. And it becomes more interesting when actually the results are somewhat intuitive, so it became clear that total effective stiffness of the bridge is one of the main factors, and then normalized axial force as well, and then also the connection. The pier deck connections of the short central piers as well. So here, well, we can see that
you need to finish soon, so please
yep.
be quick. You have 1 more minute.
Oh, sure. Okay. Yeah, and this I think this is the last slide actually. So here we show actually the confusion matrix and the tree's accuracy, and even with such a shallow tree. In this case, only with 4 levels, we've managed to have an accuracy of 96% of correctly classified instances, and this essentially shows that those features that were chosen the features that were generated and the features that the algorithm then selected are actually capable of exactly separating the two labels of pass and fail, and yeah, so this is exactly it. So thank you for your attention.
Thank you very much for the presentation. We don't have too much time. If anyone has a quick question, no. Okay, so
we can pass on the last paper. It will be a video presented by Grigoris Manoukas, presenting the paper, The Slenderness of Building in Plan as a Structural Regularity Criterion.
Of the slenderness of floor slabs in order to categorize the buildings changes into being regular in plan. Obviously, this criterion aims to ensure that the floor slabs behave as rigid diaphragms and are able to transmit and distribute the lateral loads to the vertical structural elements. The objective of the present study is the evaluation of this structural regularity criterion as adopted by the current version of Eurocode 8 and as revised in draft 3 of the new version of the code. The deformability of floor slabs depends on several parameters, such as the slenderness of the plan, the slab thickness and shape, the configuration of the lateral load resisting system, the relative stiffness of the vertical elements to the in-plane floor stiffness, and the size and distribution of openings. As a consequence, it is very difficult to define efficient quantitative criteria in order to identify whether the rigid diaphragm assumption is reliable or not. Thus, the seismic codes use simplified criteria which take into account only some of the aforementioned parameters. According to Eurocode 8, for a building to be categorized as being regular in plan, the slenderness lambda of the building in plan should be not greater than 4. Furthermore, draft 3 of the revised version of the code specifies that this rule does not pertain where the number of lines of primary seismic structures perpendicular to the long side of a building is greater than the half of lambda. In order to evaluate the efficiency of the aforementioned criterion, a total of 36 reinforced concrete buildings with various floor plans, number of stories, and structural configurations is examined. Each building is characterized by a string symbol comprising one letter and two numbers separated by a dash. The meaning of the symbols is as follows. The letter A to F indicates the floor plan of each building. The first number, 2 or 4, indicates the number of stories. The second number, 1, 2, or 10, is a modification factor used for the amplification of stiffness of the dual plane lying at the left side of the plan. For example, the symbol F2-10 corresponds to a 2-story building with the floor plan F, in which the actual stiffness of the vertical components lying at the left side of the plan is multiplied by 10. The thickness of all slabs is equal to 15 centimeters, which is the usual dimension in common buildings in Greece. For each building, 2 alternative options for the simulation of their in-plane stiffness are adopted. Firstly, rigid diaphragms, utilizing the relevant feature available in the software used. The story masses along horizontal axis, as well as the story mass moments of inertia around vertical axis, are concentrated in the geometrical center of the plan. Alternatively, 4-node cell elements are used, which is considered as the exact modeling option. The story masses are uniformly distributed on the slabs. The dimension of the square-shaped cell elements is 75 centimeters, although a coarser discretization mesh will be adequate for the estimation of horizontal displacement. This choice ensures that the nodes of the discretization mesh include all connection points of vertical structural elements with the diaphragms. In order to identify whether the rigid diaphragm assumption is reliable, the relevant criterion adopted by Eurocode 8 is applied. In particular, the diaphragm is taken as being rigid if, when it is modeled with its actual in-plane flexibility, its horizontal displacements nowhere exceed those resulting from the rigid diaphragm assumption by more than 10%. For the application of this criterion, the percentages of displacements exceedance, PI, for each point I of a diaphragm are calculated from the relation shown. The maximum value of PI for all points of a diaphragm, max PI, is compared to the limit of 10% prescribed by Eurocode 8. Negative value of max PI means that the rigid diaphragm assumption is conservative. Positive value of max PI below or above the limit of 10% means that the rigid diaphragm assumption is acceptable or unacceptable respectively. The displacements of each point of the diaphragms are calculated by means of modal response spectrum analysis method. Given that according to the aforementioned criterion, only the relative values of displacements resulting from the two alternative models are important, the use of a typical cold response spectrum is not necessary. Hence, in the framework of the present study, a single response spectrum with a constant value of spectral acceleration is applied. The seismic excitation is considered to act concurrently along two orthogonal directions, and the directional combination is contacted using the square root of the sum of the squares rule. For rigid diaphragm models, all vibration modes 6 or 12 are taken into account, while for cell element models, the first 12. In all cases, the modal superposition is contacted using the complete quadratic combination rule. In this figure, the maximum values of PI for all diaphragms of all buildings are shown. Two main observations can be made. Max PI decreases from the lower to the higher floors of each building. Max PI of 4-story buildings are always below the limit of 10% specified by Eurocode 8, regardless of the slenderness ratio or any other parameter influencing the behavior of the diaphragms. The latter observation indicates that probably the slenderness criterion specified by Eurocode 8 should not pertain for buildings where the number of stories exceeds a limit. Concerning the influence of the slenderness ratio lambda, as it is expected, the values of max PI increase with increasing lambda. This becomes clear from the figure shown here, where each curve illustrates the variation of max PI with respect to lambda, while the other parameters, namely the number of stories, the number and the relative stiffness of vertical structural elements, remain constant. It is worth noticing that compliance with the upper limit of slenderness ratio prescribed by Eurocode 8, which is 4, does not ensure the diaphragmatic behavior of the slabs, since max PI can exceed the limit of 10% in case of major difference between the stiffness of vertical structural elements. The importance of the relative stiffness of vertical elements is highlighted in the present figure, which each curve illustrates the variation of max PI with respect to the modification factor MF applied for the amplification of the stiffness of vertical components lying at the left side of the plan. It is obvious in this figure, the influence of the number of dual frames NF perpendicular to the long side of the buildings is examined. Each curve illustrates the variation of max PI with respect to NF, while the other parameters remain constant. In general, for 2-story buildings, max PI decreases with increasing number of frames, while for 4-story buildings, no specific trend is observed. According to draft 3 of the revised version of Eurocode 8, the slenderness criterion does not pertain where the number of lines of primary seismic structures perpendicular to the long side of a building is greater than the half of lambda, namely 2.75 for the case examined here. Given the results shown, this provision is not justified. The whole study leads to the following conclusions. Apart from the slenderness ratio, the in-plane behavior of slabs depends also on many other parameters, such as the number of stories, the number and the relative stiffness of vertical structural elements, and others not examined here. The rigid diaphragm assumption tends to provide more conservative results for the higher floors of each building than for the lower ones. It seems that the rigid diaphragm assumption is conservative for buildings with medium and high number of stories, regardless of the slenderness ratio. Hence, the relevant regularity criterion probably should not pertain for such buildings. The compliance with the upper limit of slenderness ratio prescribed by Eurocode date does not ensure the diaphragmatic behavior of the slabs in case of major difference between the stiffness of vertical elements. This indicates that a possible revision of this limit should be examined. The provision of draft 3 of the revised version of Eurocode date, which specifies that the slenderness criterion does not pertain where the number of lines of primary seismic structures perpendicular to the long side of a building is greater than the half of lambda, is not justified by the present study. Hence, a possible elimination of this provision should be examined. Thank you for watching.
I believe nobody has questions. Nobody raised their hand or wrote in the chat. The presenter is not here, but I believe the second author, Asimina, is here. And I'm not sure if she can answer. If not, I think you can also send a mail to the author. The organization committee will provide the
Can I ask one, just a comment based on the final conclusions? Probably Asimina can add some more things. So clearly, based on your studies, it seems that you give some recommendations for the project teams who are dealing with the development of this second generation of codes. I don't know if you, Asimina, would like to comment on this and to explore a little bit this main conclusion that could be very important for the project teams.
The slenderness of the slabs is very important for choosing the method of analysis. If the structure is regular or irregular, and these simple numerical examples show that this slenderness criterion is not valid for the structure examined, and there are many other structures that we have examined where this criterion is not valid because it depends, as we have said, by many other parameters, as the number of stories, the width of the floor, the openings, the stiffness of the vertical structural elements, the position of these elements in plan, and so many other parameters. So we can say this, we can't say so simple this criteria.
Okay, thank you.
Okay, so with this, we conclude this session. If you have any more questions for the authors, you may send them by email to the authors. And I assume that we have 15 minutes break, right?
Yes.
Okay. So thank you very much.